Lab 3. Introduction. In this experiment, I investigated the behavior of DC and RC circuits using circuit simulation. I applied the principles of charge conservation and energy conservation to analyze current, voltage, and capacitor charging and discharging. I then compared my observations with the theoretical predictions to see how well the model represented real electrical circuits. So some of the physics concepts I used was charge conservation, where I1 equals I2, energy conservation, where the sum of all voltages equals 0. Ohm's law says voltage equals uh, resistance times the capacitor, and then series resistance, which is RT equals R1 plus R2. Capacitor voltage VT equals V naught E raised to the negative T of RC, and then capacitor voltage, which is tau equals RC. So the systems and surroundings. The system is the electrical circuit, including the battery, resistors, capacitor, and connecting wires. And then the surroundings, I said, was the surrounding air, the simulation environment, the light bulb, and the person taking the measurements. So for the lab, this picture is of my second circuit that I built. And for the lab, the experiment began by assembling a series of circuit connecting two batteries, two resistors, and two ammeters. The current and voltage at different points in the circuit were measured to verify charge and energy conservation. Next, an RC circuit was constructed using a battery, resistor, capacitor, and a light bulb. The charging and discharging behavior of the capacitor was observed by measuring the voltage over time. And finally, the collected data was analyzed to calculate the RC time constant and compared the experimental results with theoretical models. So this is my result. This is my graph. I have my time here across my voltage, and then the calculations in between. So for my calculations, I did the time constant, which is just tau equals RC, where tau equals 4.7 seconds. The discharging capacitor equation, which is just VT equals V naught e to the negative T over RC. RC is 4.7, so that's VT equals 9 e to the negative T over 4.7. My linear apply calculation is just ln V over V naught, which is equal to negative T over RC. So ln of 2.5 over 9 equals 1.28. To calculate the slope for RC, the slope is equal to negative 1 over RC1. So the slope is going to be equal to negative 0.213, where RC is going to equal negative 1 over slope, so RC equals 4.7 seconds. And the first what if question was, what if you were doing this experiment in real life and you use an actual ammeter instead of an ideal simulated ammeter? What's the difference about the real ammeter, and how would it have affected the circuits you hooked up to? I said a real ammeter has a small internal resistance, so unlike an ideal ammeter, which has zero resistance, this slightly increases the circuit's total resistance and causes the measured current to be slightly lower than in the simulation. This difference, I said, was usually small and shows that real measuring devices can slightly affect the circuits that they're connected to. And the second one of question was, what if you're doing an experiment in real life and you use a real battery to charge a real capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach the full charge? Would this prediction happen in real life? I said that the ideal model predicts that a capacitor connected directly to a battery with no resistance would charge instantly because there's no resistance limiting the current. In reality, though, this cannot happen because real batteries, wires, and capacitors all have internal resistance. So these resistance limits the current, so limited current, so that the capacitor charges very quickly, but not instantaneously after a large initial surge. So in conclusion, this experiment demonstrated how charge conservation, energy conservation, and Ohm's law can be used to analyze DC and RC circuits. The measurements and calculations closely match the theoretical predictions, showing that current and voltage behave as expected in series circuits, and that capacitors charge and discharge exponentially over time. Overall, this lab provided a better understanding of circuits behavior and a difference between ideal models and real electrical components. Also, I noticed that my theoretical or my calculated predictions were closely matched to theoretical predictions. So this showed that even though in real life, with the resistance and other stuff, that you can still use these calculations to maybe build circuits and use them as real engineering projects.